So it's a pleasure to have Xinwei Deng today talk to us. He's our old colleague and friend from Virginia Tech, outstanding statistician. He's done a range of different things on not just epidemiology, but also problems in operations research and such. So I'm going to let Xinwei describe the work he's doing today. And we'll take questions after it's done. Thank you so much, Xinwei, for agreeing to do this.
So thanks much for the invitation. As Madhav mentioned, I have known Madhav and his group for a long time, and we have a lot of collaboration on epidemiology and machine learning, statistics modeling. I enjoy a lot. I call how the statistician understand the science and understand this epidemiology more. So in today's talk, I like to share some my recent work on this I call new type of data, or kind of unconventional type of data. This is not directly related to knowledge, but it's highly related to I call operation, also as well as its healthcare and some drug treatment. So the data I like to mention, or the problem I can mention, I call it QS factor, represent for quantitative sequence factor. So I will give you a brief motivation why call this quantitative sequence. Basically involve not only like numeric variables, but also involve I call sequence variable, or actually the order about the variables. So this is John work with two friends at the UGA. So here's the outline. So before the talk, I like probably give you a few I call random thought about the data science or about analytics, since I'm a statistician. So nowadays people talk about the data science, talk about data a lot. And as a statistician, we always try to think how a statistician should be involved in data science. And there are many things actually I learned from Madhav and his group to see how a statistician or a non-traditional statistician to work with the science, with engineer, and with different disciplines. Then we'll talk the major things. So one thing actually I realized nowadays, every time when I give talk, and I found it's hard to see the audience, because usually before pandemic, we go to more like the physical meeting, we can see the face. People laugh, people frustrated, people take a nap even. Then we see, oh, we should talk about some joke and try to refresh the audience. So now it's harder. So the thing then I try to notice, so every time when I give talk, try to talk a little bit, I call non-technical things. So this is my non-technical. I call my recent data points. So left one is my 3-year-old kid. And sometimes he will grab my AirPod and do something for his fun. So I call this is more normal data. And the right one is photo of me. It's more like beside this stay at home. Occasionally we go hiking. As you know, Virginia Tech is surrounded by all these nice trails, as well. Of course, UVA also have many nice trails. So I occasionally go to hiking to refresh the mind, then come back to work. So here is my, I call 2 cents about data science. As a statistician, we always think about, we deal with the data. But from a data science perspective, or from a big data perspective, actually, our old thinking about the statistician is, we think data is there. Data is already there, we just like a data matrix. We do the modeling, do the analysis, do the inference. Okay, so oftentimes we say our data science, or I say a statistician oftentimes focus on this part, I call modeling, right? We say we build statistical models, we do model estimation, we do model inference, or we do modeling prediction. But now I think as data science and this big data wave come, people try to think more and more. So as a statistician, we also try to think a bit more. So that's my view is like, oftentimes we say this, first of all, we should understand how the data come from. Probably that's actually very crucial, right? So because how the data are collected and how the data come from, actually we're driven all the things as the original, right? From data, how the data come up. So in statistical world, this part oftentimes we call data collection. But now is people may think, okay, they're big data. A lot of data already there. But clearly how data collected is still very crucial, no matter it's big data or small data. Since once we understand better about data, then we can come out better about modeling, or better feature extraction, or better decision. Thus, I think it's more like we probably, toward the data science, we should approach more about data collection, approach more on the data generation mechanism, really how data collected, how our data are generated. So from the data perspective, then we start to do the modeling, which I call second module. So second module is what we traditional statistician do, or we traditional people do is say, okay, suppose data there, you do processing, you do feature extraction, then you try to build a model. You can build a supervised learning or unsupervised learning or other things we call the modeling. But as I mentioned here, so once we think about data science, because data science itself is truly interdisciplinary, as well as its computational knowledge about these centers. So it's quite interdisciplinary. It's not like one research area or it's one discipline can handle everything. We need expertise from data, from computer science, from domain knowledge, from policymaker, from infrastructure, so on and so forth. So, which means oftentimes, as I say, for statisticians, we focus on modeling. We say, okay, we have a good model, have good inference, good prediction, period. But I think reality and towards data science is not in that case, which means essentially the model should be used appropriately, used wisely. That's called the decision making. So I feel that, so it's along this line, understanding modeling or to evaluate the modeling, it's very important to say how the model are used, which means how the decision making involved with modeling. So then from the decision making, which oftentimes, or actually not oftentimes I say in the conventional way or intuitively, we say the decision making or decision optimization should go back to infer how to collect more data, or to infer the data quality more, or to infer understanding about the data. But I say not often, is because oftentimes, like in research aspects, it's like once we have model, we give the decision maker, say, okay, you can use our model in what fashion. Then there's no follow-up. Oftentimes, not much follow-up. But clearly, I can see by close this loop from data, modeling, decision making, back data, that's probably is a good angle toward the data science. To really try to understand the data, infer the data, use the model based on data, and back try to give us better understanding about collect data. I see, for example, in this COVID-19 pandemic, I can see such closed loop probably can be very useful. Which is really say, we cannot say make just some inference based on the data we collected. We probably should understand more is say, when we make an inference, we should understand how these data are collected. When we present our modeling, we should think a little bit more how the model are constructed and how this connect with decision making. So along this, I call data modeling and decision making. So by recent research interest, in these two folds, I call one is say interface between experiment design and machine learning. It's really say from data collection perspective, even at data collection stage, we should think about modeling, how potential model will be used for analyze the data, such that your data collection can be more efficient. And from modeling perspective, when we try to do the machine learning algorithm or analytics, probably we should think a little bit more or try to understand a little bit more how data are collected, such that your model will be more meaningful, more interpretable, more explainable, so on and so forth. So the second folder about I call the joint effort between modeling and the decision making, actually I call it decision integrated modeling and optimization. It's really say when we try to build a model from the data, probably we also need a link or to reflect by the decision making. Actually, we have Achla, Anil, and I, and also a few colleagues, we have a joint work I call decision adjusted modeling for this solar panel adoption in this rural Virginia area. So that's probably is one example how this decision should be come into your model, such that your model can be better used in the decision making. Another aspect I can see is this decision adjusted or decision integrated framework can be broadly back to more ethical issue about data. For example, we want the model to be more fair. So essentially, this fairness is related to a kind of decision making or optimization, because the way you use model cannot be biased. So that's why you want to put fairness back to the model. Same thing about the cybersecurity, because when you build a model, probably you are not just consider about estimation inference. You also need to consider about the cybersecurity issue, privacy. So all these things is part of, I call decision or broadly about the decision. So in a short summary, I call my 2 cents is like, really, we should appreciate more about the data part, appreciate more about the decision part. As a statistician, that we can enhance the way we do the modeling. Okay, so here is just I call a funny slides, I call this towards data science, to be or not to be, to be. So first thing is clearly this computational epidemiology, data science is truly interdisciplinary and a challenge. So I always try to think, how shall we prepare for that? How shall we more appreciate for that? So that's I call it to be and not to be. So I call to be is, I say, to be a statistician, because statistician always try to think about the data, think about the data generation, think about the probabilistic framework. So the good thing about the statistician is always try to build a model from probabilistic framework. So the probabilistic framework clearly can enable the modeling and inference, which means we not only care about prediction, we care about uncertainty. Like you predict tomorrow temperature is 90 degrees, is not very useful unless you have a quite confidence interval. So the second point I call is an aspect about data generation mechanism. I call data generation mechanism is really look from a data point's perspective, one data point, another data point, another data point, they can be correlated, which means they have some generation mechanism. And from the features, which means one feature and another feature also can be dependent, which is that's another angle about data generation mechanism. And such things can be extended to say different source of data and the data collect at a different time, different location. All this one essentially reflect, I call a generation or how the data are collected a mechanism. Regarding the not to be, I say toward data science, probably we should not just be a statistician. I say traditionally statistician just focus on modeling, focus on inference, but not just be a statistician in a two folds. One is say, really, I think toward data science, it broad our scope. We should appreciate more about ecosystem thinking. So the way about system thinking is really say, okay, once you see the data, we should understand the original motivation about the problem, why people collect such data, and what kind of question to be addressed. From then to the modeling to the decision making. Essentially, I would say it's like toward a closed loop of data, modeling, and the decision making. Okay, so now let's move to about the problem I like to talk. So this one I call quantitative and the sequence input. So essentially, there's some experiments or some data involve multiple components arranged in a sequence order. Okay, so let me give one example, probably to better illustrate the idea. So in this kind of treatment of certain disease, so suppose they have like 3 anti-tumor drugs, I call A, B, and C. But this treatment essentially say they try to put these 3 drugs into the object in a sequence order. For example, maybe some people may like take A first, then after a few hours, take B second, then take C last. Okay, so this is I call arrange this add sequentially with different dosage. So in other words, which means you can think this is like more like a combinatory treatment. So you put the multiple drugs in different orders. So the response basically is the percentage of tumor inhibition, the larger the better. So you look here, so the table is try to illustrate part of the data. So this data you can see, okay, you for example, so first row here basically say you can put the drug A first, okay, then drug B second, drug C third with different dosage. Then you get the response. So then you compare with experiment 2 or round 2. So you'll see all the same, still drug A first, drug B second, drug C third, but dosage are different. Dosage are different. Clearly, you say different dosage will affect the response. But if you look at the round 3, the third experiment, so you'll see all the dosage are the same. Drug A is the same dosage as here, drug B is the same dosage as here, drug C is the same dosage as here, but all are different. So all the basically drug A is the first, drug B is third, drug C is second. So in other words, which means the order also matters. So we call this one, I call QS factor, represent for quantitative sequence output. So the underlying basically try to say, in such experiments, order matters. Which component first, which component second, which component third, matter your response. The second message, basically quantity matters. Of course, the dosage also matters. So I would say such data essentially is kind of interesting is because if you ignore orders, then it's just a multivariate vector, right? Multivariate vector about the dosage for each component. If you ignore this dosage or quantity, then it's about essentially the sequence. It's sequence order, which is really about arrangement of multiple components in a sequence order. Of course, we know order matters. So for this QS factor, clearly you can see order matters, quantity matters. And such kind of data is not only in these drag experiments. You can see it's also observed in this operational. For example, you put multiple package with different price into a bin, then which one first, which one second, so on and so forth. So clearly such I call QS factor is interesting. Interesting we see is the different quantity about this drag affect response. Different sequence order affect the response. And moreover, it's not a traditional like a continuous factor, not a traditional categorical factor, because original categorical factor is more like level 1, level 2, level 3. So you have a blue, red, yellow, so on and so forth. So, but here is the order, but it's not traditional about like the ordinal variable, like very spicy, or not spicy. It's about a sequence, about order, or more precisely, it's about permutation, right? Permutation of multiple components. So in that sense, actually, it's interesting on these QS factors. It's involved I call semi-continuous and semi-categorical. So the objective from a modeling perspective is there are two things. One is I call modeling. So we try to model the relationship between input and output, okay, oftentimes as a supervised learning. So the input is so-called this QS factor, involves the sequence order as well as the quantity. The output basically is the response. Here is incubation. Then the second one is say, you can imagine if there are multiple components, there are so many possible combinations. Essentially, it's very hard to do a through experiments to go through all permutations, as well as go through all possible quantity or dosage. So that involves the second things. You say, back to here, suppose we want to find the optimal setting, which means optimal sequence order and optimal dosage, such that to maximize this response. Oftentimes, it's try to like most improve the effectiveness about treatment. Then we may wondering say, are we going to do a lot of experiments, or are we going to collect a lot of data, try to go through all possible, all the sequence, all possible dosage? So clearly, answer is not trivial. So which means back to the I call the second goal. So second goal basically say, can we have a more effective to do this, optimize this dosage and the sequence order, such that try to maximize or optimize certain objectives. So that's what we call active learning. So I say it's a well-defined objective in terms of modeling and active learning, but clearly it's not a trivial job. Not trivial job is because given these K components, it's not possible to go through all factorial of experiments. Plus, there are also quantitative part involved. So we also need, I call a good design of QS input, which means if you say from a modeling perspective, we want to form a training data set, but forming a training data set is not trivial. We cannot just like random collect the data based on random permutation, random things, the random combination about permutation and quantity. So that's about a design, I call an initial design or code start problem. So the second part is this mainly about this talk, is how can we build a model and active learning strategy for this QS factor, involve both quantitative factor and this sequence factor. So here is I call this QS learning, basically try to say, how do we do this modeling and active learning involve this quantitative sequence factor. So this framework basically is say, okay, we want some initial design. Because of time limit, I'm not going to talk a lot about this one. For people who are interested, we can talk more offline. Then if you have initial design, which means you get the initial training data, then you can build a model. Actually, that's the one we propose. We call MAGP, the surrogate model. For the surrogate model, it will guide us, say, what kind of acquisition function we want to build. For example, you can have expected improvement and all other things. Then it guides us try to collect next experiments or collect next data or looking for the next setting we want to explore. Then we do evaluation, and then we can continue this loop until certain criteria is satisfied or until the budget is satisfied. So oftentimes in the real data collections, oftentimes it's restricted by budget. maybe like if you only can afford 100 rounds, then you probably through this active loop of collect data, then up to 100 rounds, then we get the solution. Okay. So some notation, first of all, I think from a modeling perspective, first thing is we want to formulate the problem about this QS factor into something we are more familiar with or we can handle. So we use this notation I call W, represent for this QS factor. So I say this QS factor involve quantitative and ordering. So well, the first law is about their order, which means what's the position of C1, what's the position of C2, what's the position of CK for this component. Then corresponding, what's their quantity. Okay, so essentially, first law represent their permutation order, second one represent their corresponding quantity. So I use this OI and XI represent this order of arrangement as well as their quantity variable. So let's give one example. So example here is say, if you look at this round 3, so you have drag A, drag B, drag C in the order of drag A first, drag C second, drag B third. So that's why this order is 1, 3, 2. Right? A on the first position, B on the third position, and C on second position. And corresponding, they have this quantity, so 3.7, 95, and 0.16. Right? So that's represent 3 quantity for these 3 components or 3 jack here. As I mentioned here, is the challenging part is this WQS factor is semi-continuous and semi-discrete. And this discrete is not like ordinal or categorical. It's about permutations. And we know permutations from a mathematical perspective, it's like back to permutation group. It's quite complicated. But how can we model the relationship between this WQS factor and the response, the outcome? So that's the first objective. So first objective is really how can we build a relationship, a good modeling for this Y response and this QS factor with accurate prediction and meaningful interpretations, because we want to understand what's going on there. So second one is how can we efficiently find this optimal setting? I call active learning. Try to find the thing. For example, generally either minimize or maximize. Minimize your response or maximize response. What's the optimal setting? Because remember, this Y essentially is a black box functions because you don't know exactly what's the surface. Yes, and oftentimes does not have an explicit form. And moreover, such kind of response surface essentially is stochastics in nature because they involve uncertainty. Let's start from modeling, and if time permits, I will talk more about active learning. So for the modeling perspective, actually, there's some literature people try to do so. So one literature, I call this called PWO, called pairwise ordering. The idea essentially is try to say it's hard to understand the permutation order or a sequence order, but it's much easier to understand the relationship between 2 elements, 2 orders. Right? So, for example, which means this PWO is trying to say we can try to transform this permutation or this order sequence into a sequence of variable, try to compare each pair. So basically say if your OJ is smaller than OL, which means for component A, the order is smaller than component B, then we say positive one. Then otherwise we say negative one. So essentially it's pairwise. So for example here, so if your order is like 1, 3, 2, which means drag A first position, drag B third position, drag C second position. Then we can compare one position A and B, A and C, and B and C. Try to see which one is before the other one. That's why we give this like the Z become like Z1, 2, compare component 1 and component 2, Z1, 3, compare component 1 and component 3, Z2, 3, compare component 2 and component 3, regarding their order, which is earlier than the other one. That's pretty give you this all kind of indicator value 1 or -1. Clearly, this is a one approach, try to mapping this permutation order into, I call this PWO, this pairwise ordering. But one thing, if you think a little bit, you'll see there's some good thing or bad thing. So this good thing is like, essentially, you try to transform a permutation order into a pairwise thing. But the not very good thing is there that such kind of mapping is not one-to-one, which means given any these kind of factors, does not mean you can always come back to permutation. Moreover, such PWO is not easy to incorporate the quantitative part in, right? Because it's really try to deal with about the order or permutation orders. So what we try to propose here essentially will borrow some strengths from this Gaussian process. The Gaussian process essentially is more statistics modeling, try to model relationship between input and output using this kind of stochastic process idea. So the way we try to propose, we call mapping-based additive Gaussian process. So why is this called MAGP? So the idea basically say, since we have permutations, and we have permutation involved these orders, we're using this additive structure try to understand each order how they play a role, or the order of each component plays a role. Okay? And we're using this Gaussian process because that's flexible to quantify the complex relationship between input and output. And we're using this mapping-based approach. So essentially, it's because this order things is discrete by nature. So you cannot like directly input into your Gaussian process because Gaussian process essentially is more like a continuous process. And the potential challenge essentially is, say, if we do more like blood and tooth, it can involve a larger number of parameters, maybe over-parameterized or too many parameters. So here is some brief about the Gaussian process. So I will briefly just mention the idea about GP. For people who have familiar with that, then probably you see very clear. So Gaussian process basically try to say, okay, your response is a function of X, essentially involve can be C. Behind that have a Gaussian process CX driven. And this Gaussian process is more like say, okay, give each data point, each data I call X1 up to Xn, they are involve a process, which means they always correlated with each other. So in a simple version, you're saying give your input X1 to Xn, then the realization about this Gaussian process become a random vector, follow a distributions. Since it's a random vector, they follow, for example, normal distribution. That's why how this Gaussian come out. So from a multivariate normal distribution with a mean, I call the zero mean. And since a multivariate normal, so involve covariance functions. And more precisely, here the sigma square is variance, and R represent the correlations. So basically, it means, as I say, at a realization, so each observed response are correlated with each other. And the good thing about the Gaussian process essentially is easy enable this prediction and the UQ, so-called uncertainty quantification, because now we think every response are correlated, even give a future response that's correlated with the past response, which means the response you want to predict is correlated with the response you observed through this joint normal distribution. That's you can easily infer what's this prediction at the future. So that's this prediction mean. And here basically show a simple illustration about how this prediction looks like, and also we can enable this uncertainty quantification through confidence interval and other things. So the proposed MGP essentially for this QS factor, I will say here we adopt an additive structure. So here you can see an additive structure. So the additive structure is try to emphasize this G1 up to GK are independent Gaussian process components. And each component try to reflect the impact of each component in your permutation. Right? So that's a nice way essentially say, in order to say you just build a blindly or like a black box Gaussian process, we try to have additive structure such that each Gaussian process component corresponding to each component about in your sequence or in your permutation. Then the remaining thing here is say, once we have this additive structure, then we need to specify, since we have K components about Gaussian process, each component need a covariance structures. So that's the equation here. Try to specify the dependency about the 2 points. So generally speaking here, it's like if you have continuous part, so remember X are continuous part, that's easy. That's traditional Gaussian process. They say, okay, if 2 points are close to each other, they are more likely to correlate it. Then, but about here, that's about the ordering. Then the ordering things, we say, intuitive speaking, we'll say, okay, if they are ordered close to each other, they may like more like to correlate it. But the issue here is say the order itself doesn't have any numerical meanings. Order 1 and 2, right? It's just about the order is no numerical meaning. As I say, this order sequence is not a numerical variable. We may is more like it's kind of categorical, does not have some numerical meaning, but not exactly numerical meaning. We cannot say, okay, just here replace their order by the observed order 1 minus order 2 means they are closed. So to address this issue, what we introduce, I will call it's, as I say, the sequence order or this permutation is discrete in nature. What we propose here is say, if it's discrete order, you just like think you have a blue, yellow, and red. Maybe like you have a kind of order things, kind of magnitude things. So it's discrete in nature. What we address, how to address them is like we consider a mapping. Basically, you say you can think you can map blue into some number, red into some number, yellow into some number. But how this number should be, we don't know. So that's essentially follow the idea about this latent variable or these hidden variable things. So we consider mapping about this order into a latent vector. So that's illustrated by the matrix here. So basically, you can think you have order 1, 2 up to k. You're mapping into like first column, second column up to t column. Depend how you want to model it. So, and to avoid over-parametrization, basically we allow this like upper portion triangular to be zero, to enable model identifiability and simplify the model structure. By doing so, essentially, say we are thinking about this order. The order or the order sequence are driven by a few latent variables. A few latent variables are constructed here, and we know regarding permutation, essentially is once this number of column is up to the number of permutation numbers. So essentially, that's will be sufficient, and oftentimes probably can be fewer. So here is just one example. So this example basically say, suppose we consider experiments with like k components, k operation in a production line. Okay. Then they have like fixed locations, and we want to assign the operations. Okay, assign the operations. Which operation you can think operation is like C1 up to C4. These 4 operations should be arranged into these 4 locations. So clearly, that's a permutation things. And such things actually is widely observed in this operational research and the logistic or supply chains. Then you'll see, for example, you have position 1, 2, 3, 4, mapping two vectors. 2 vectors that involve the 5 parameters. And we treat these are latent variables or latent parameters, and which will be estimated via this we call MLE, is like maximum likelihood estimation. Or more generally, those parameters will be estimated through our learning algorithm or through this loss function or risk functions. There are a few properties. So why we use this MAGP? So a few properties, they say, because of this mapping, we can project this order into a t-dimension latent vector. So the t-dimension latent vector then it becomes more like numerical vector into the Gaussian process, into the modeling. Okay? Provide some flexibility to quantify the impact. So second one is say, actually, because of the Gaussian process, we can construct this covariance function for the response, not just only for each component in an additive form. So this additive form can give us better idea which component, which means the order of which component is more important than the order of other components. And also it can guarantee this covariance matrix to be positive definite, because from estimation perspective, it's crucial to have this positive definite. Remaining things essentially is quite, to some extent, it's kind of straightforward. Although it looks kind of a lot of formulation, but it's relatively straightforward because we can do this parameter estimation through this minimize the negative log likelihood. Also, you can through minimize the other loss functions. And we can use this analytical gradient to facilitate the computational and parameter estimation in the optimizations. And we can also have this prediction mean and variance because of this Gaussian process. And moreover, because of this Gaussian process, we can do this uncertainty quantifications. And this uncertainty quantification means more precisely, we can provide a predictive distributions for the new target or new input. And because of Gaussian process, we will be follow normal distribution with explicit mean and explicit variance. As I say, actually, this UQ part, why we adopt this Gaussian process, actually lays a very good probabilistic foundation or probabilistic framework for this later active learning. So here are some one numeric example. Try to see, does this MAGP or this proposed modeling perform well? in terms of prediction aspect. So we consider this example from an operational perspective or logistical perspective, which means actually we say there's a single machine scheduling problem. Basically, it's like you have a machine, but you have multitask. You have like multiple jobs. Then you need to decide which job go first, which job go second, which job go third, so on and so forth. But clearly, the cost depends on how do you arrange these jobs. So here is the data. So we have 6 jobs. So each job have some processing time. So this, for example, is a permutation orders. Okay? And based on your permutation order and the processing time, there is I call cost functions. Of course, the cost function cannot be linear. If they're linear, then things are easy because that does not matter related to the orders. Of course, oftentimes it's not linear. As I say here, essentially, if not linear, here we use this the Townsend 1978 paper, classical paper. So if it's quadratic function, then we can invest the prediction looks like. So we can generate all possible permutations. So here, actually, we even don't consider quantitative part. So all possible permutations, then we can have like a training and a test to do the comparison. So clearly, you can see the MAGP here, which is 2D, basically is 2-dimension latent vector. It's full, basically is up to k-dimensional latent vector. So we are see the 2D MAGP and the full MAGP perform much better than the other 2 approach, so which using this pairwise ordering. And also we are see oftentimes like this 2D mapping is sufficient to do a good job. The numerical example basically try to illustrate the MAGP have a good performance on the prediction. But it's not the end of story. Basically say, yes, so it's MAGP can do a good job, but it's not possible in practice, for example. It's not possible go through all possible sequence. Plus, you have quantitative part. Which back to this, the question is why we want active learning. So in practice, which means running experiments is expensive. Also, time is important. And so it's not practical to run all possible experiments for this W. Remember, this W involve about sequence order. For example, if you think about k equal to 10, if you try to arrange 10 jobs in a sequence, then there are so many possibilities. 10 factorial is already a huge number. Plus, you also have the quantity. So you need to choose different combination about the quantity associated with the sequence. So if you consider 2 things together, the number of possible runs can be easily huge, even a small number of components in your experiments. So that's a thing which means just call for, say, from a data collection perspective, are we going to collect data more static or more adaptively? So that's what we call active learning. Basically try to sequentially collect the data to find the best setting of QS effect. We start from a small long size experiments, collect a small training data, then we build a model. So from the model, we try to guide us, try to select next design to collect data, then continue this procedure. So this proposed QS learning essentially adopt a few things in the literature. So essentially we define improvement functions, which basically try to, for example, for the minimization problem, we say, okay, current minimizer, the smallest value is here. If we have found a next data point such that have a smaller response, we take it. If not, then we just treat 0. So that's how this acquisition function are built, which try to encourage, try to find the improvement in terms of find the minimum values. Then, as I say, everything here, this Y is actually stochastic in nature. It's not a deterministic system, right? So, because also we don't observe this YW for the future. So those things essentially involve the expectation, which means expectation regard this uncertainty about the future observation. And good thing here is like we do have some prediction or predictive distribution about this future. So that's why they call this expected improvement. Future essentially is a predicted distribution based on current observation. So by doing so, essentially, good thing here, as I say, is involve the integrations, involve this improve functions, involve this predicted distribution. Fortunately, because the Gaussian process lays a good foundation for this uncertainty and the probability distribution, we can have a closed form about this quantity. So this expected improvement essentially have a closed form, involve the CDF, PDF of normal functions, involve the mean and variance about the predicted distribution. But nevertheless, it have a closed form. And actually, The interpretation about expected improvement is involved a thing they call exploration versus exploration. Roughly idea basically say, when you try to zoom in to find the minimum value collocations, you want like look the gradient descent direction, but as well as open your eye, try to explore other regions. Okay, so by doing so, essentially it's QS learning, which means give the current data, so we can build a model, MAGP model. From the MAGP, we have a predictive distribution. From there, it will guide us, try to find the next data points. Next data points, try to maximize the expected improvement. Okay. Then we can evaluate the response at the new selected location or new selected design. Once we have the new data points, then we can update the model, which means refit the GP, and we can continue this procedure until the stop criteria. So in other way, which means this QS learning is more like adaptively or sequentially collect data points. In other words, in an illustration, suppose my budget is just like 100 rounds. So we may say we use 10 rounds as an initial starting. Then from 11th to 100, we do sequentially. Collect one experiment at a time, then evaluate, then check to see how the next data point should be collected. Here is an algorithm. So because of time constraint, and I'm not going into detail. So the key thing or the challenge is here, because this QS factor involve both continuous and discrete, or both quantitative and orders. So here we borrow the idea is more like coordinate descent. So when we search these optimal settings about maximize expected improvement, with like given O, we can search X, given X, we can search O. Then we do a few things. And also there are also a few more like polished things, how to search the discrete part. Here's a case study. So the data essentially is come from this Wang et al. 2020 paper. It's a recent paper. So in their examples, they have 24 rounds about this cancer treatment, involve 3 drugs. So they are A, B, and C. So for these 3 drugs, actually they perform all sequence order. Remember these combinatory experiments, like you put A first or B first or C last matters. This in vitro experiment is performed on this larger cells. Yes, and in particular, what they do is like each drug, which means each component, add every 6 hours. Okay, and the response are collected after the last drug added and waiting for 6 hours. Okay, so here is 2 things. One is try to evaluate. Suppose we use this all available data and we chop into training and test, then try to check how the good performance is. So clearly we'll see this MAGP can perform better because they are more flexible. Also, we have a, I call, more interpretable structure through this additive structure on the modeling. And here are evaluation about the QS learning, because in this data, we have these 24 rounds, which means we know actually from by look all available data, we'll see this largest 4 response is like these 4 values. Then we start like 8 rounds as initial, then we do this our QS learning to select the 7 sequential rounds. Actually, up to the 7 sequential rounds is a stop. So the left panel show how this expected improvement looks like. And you will see at 0.5, the expected improvement are slow, very marginal, which indicate probably can be stopped. And the right one try to see what's the cumulative maximize, which means among these 1, what are the maximize at each stage. So clearly you can see up to 7th, actually you can find this good way. We also do some, benchmark comparison. So one is people will easily think, how about just do random search? So clearly, actually, if you do random search and keep the same round size, you'll see actually we can prove that the probability to include the optimal setting is more or less as just random search. Actually, it's just like 50%. A little bit more than 50% is because of the round size here, but you'll see more than 50%. We also compare a second benchmark, basically is uses pairwise ordering. So you'll see actually oftentimes they are may not able to catch the things. And where of that, the PWO essentially is not naturally incorporate this quantitative part into the model. Here's the summary. So in this work, as I mentioned, I think what I would like to share with you is say, in many this kind of modern experiments or modern data, it's not only like quantitative, not everything is numerical variables. There's some variable is categorical. Actually, it's not just only categorical. Some variable involve orders. So in a simple summary, I call often, so such data order matters. quantity matters. The second one here is say, once this order involved, actually the data can be huge, or the experiments can be huge. Even the computational power, even in the compute experiments or computational epi-knowledge. So the all possible combination is not practical to go through. Then we'll think, how can we have more like active learning, more this kind of adaptive thinking about collect data or try to find the optimal set. So there are a few interesting directions. So one, I would say, clearly the responses are not limited to the continuous response. There will be non-normal response, there will be categorical response, there are binary or counting, so on and so forth. So the second thought here is say, actually the current one we use is mapping things. But as you can see, this mapping idea is try to map sequence order into some latent vector. Clearly that can be potentially, it's like the identifiability, the model complexity. So here currently there one ongoing work with my students is we propose something called QS transformation, such that to simplify this Gaussian process model. Thanks.
Thank you very much, Xinwei. Great.
Sure.
Yeah, great talk. I really enjoyed it. Can you say something about the number of rounds of active learning you would need? Like, are you able to get some bounds based on the data and so on?
Yes, that's a very good question. Yes. So far we don't have theoretical bound yet. So the reason is because this acquisition function is expecting improvement. So this experiment actually there's no guarantee you can find the optimal setting. Of course, the practically essentially perform very well. So in order to, if we want theoretical understanding, like how many sequential iteration we need, probably we need to change acquisition function. One possible acquisition function actually is quite well known. It's called UCB, the up confidence band. So widely usually on these multi-arm band problems. So I think from the use, probably by adopting UCB, it's better serve, a theoretical foundation to investigate regarding this convergence and the upper bound for iterations.
In one of your early examples, you showed 3 different treatments and the orders of these treatments. Suppose there were more than 3 treatments, but you knew something about some of the interactions between treatments. So suppose you had like 200 treatments or some larger number, but there was known constraints between pairs, like C had to go before D or something. This sort of, number one, is that sort of question even useful? And number 2, could your method handle that, introducing constraints?
Oh, very good. Actually, yes, very good question. So the current framework by this mapping, using this like a sequence order mapping to these latent variables, probably it's not very easy to do this constraint. And I mentioned in the last slides, I have ongoing work. Actually, I was revise the paper in the mornings. So use this QS transformation, we are able to impose the constraint on the orders. And the key idea about QS transformation is it's not hard because a sequence, essentially you can transform to permutation matrix. So we can impose some constraint on the permutation matrix to enable such objective. Chris, it's a very good point. I think essentially it's like if the number of components is very large, we may have actually this the part we haven't talked about is like we have to have a good design in the beginning. Otherwise, it's very hard to do the job.
So my question is, if you actually have a causal model, it could be a process model, or it could be a physical model, or a biological model, something that is like a quantitative or a computational model. Can you constrain the analysis to reflect those kinds of dependencies and limit the size of the experiment or something like that, right?
Yes, that's also a very good point. So that's essentially we call calibrations because remember, the model we currently build is more like a surrogate model. You think this like the real experiments is more like black box. So if you have some like real data, as Chris mentioned, have like some physical experiment, those data can guide or calibrate the surrogate model to make this modeling or active learning more efficient.
No, I actually meant a physical model, like a differential equation or a system.
Oh, model. I see.
So it'd be great if you had the data, but suppose that's the point is you want the data.
Yes.
But it's a gigantic experiment and you have a causal model. right? Because so what I'm getting to is the relationship between sequentiality, cause, and observation, right? This is like, I think it just seems to me that if you could constrain the statistical requirement, the collection requirement, statistical model by the causal model, by the, say, let's call it the theoretical.
I see your point, yes. Yes, that actually will be nice. It's because that essentially like, if from this partial differential equation or this physical model can give a restricted region about the feasibility, that will be better served about this active learning or the model the relation. Especially like you mentioned, like this sequence, like Chris mentioned, like 200 components in a sequence. So it's very hard. Probably they have some like this physical model or this partial differential equation, give some idea what kind of order is preferred, what order is not very likely. Yeah, very good point.
I think this is like really, really interesting work, really, seriously.
Yeah, I personally, I like this. I mean, I like this piece of work. It's like, it opened my eyes to think about order matters. But when the order comes in, there are many interesting components into the basket.
Xinwei, I'll ask a question as well. So fundamentally, you take the order and you reduce it into a numerical form by using these vectors. And I don't think I followed all parts of it, but I get the basic picture. What if I were to do this, what are the properties of such mapping that one would want? And if I want to make an axiomatic treatment of this, right? Because a general issue, you take an order of, and map it into a numerical part. I think an axiomatic treatment which says, here are the desired properties of these numerical vectors that we would like. Would you have anything on it that you've thought about? Because I think that's central to the story, because a lot of interpretation then finally happens in these numerical quantities again.
True. Okay. Yeah. Very good point. So yeah, this one is, I think, potential drawback is about this latent vector is not easy to interpret. Of course, we may able to do something by this like estimate latent vector. Once we project to this Euclidean space, we may see some patterns, but there are no direct things. That's actually like in this ongoing work I got QS transformations. I want to do more like direct mapping from this QS factor mapping to some matrix. Actually, I got generalized permutation matrix. Then everything is one-to-one mapping explicitly. That will be served much better in the interpretation.
Right. Something that basically says, I don't know how to do this right now, but something which says I have this order. If I take some suborders, then certain properties have to hold. If I take, flips, then certain properties have to hold. So I think if we have those axiomatic characterization, then the numerical thing that get mapped will have a certain amount of meaning to it. Otherwise, it seems, for a person like you can do a good job. I cannot do a good job right now with it is the point. So okay.
Yeah, I think like the current one is like we may able to do some post inference, but I do admit it's not kind of easy to understand.
Okay.
So it's not easy to understand because really in a system like this, what matters is the total order, and suborders might not pick in, or what? I mean, what is it that makes it hard to understand?
Yes, that's actually also very good. So that's, I think, one thing is like you see this pairwise one is easy to understand to some extent because they only care pairwise, right? So the one we are doing this latent one is actually we are consider about like a global ordering structure. We may incorporate, by doing this latent variables, even you can think we can actually project part of the sequence into some order. Then that can be do the more inference, more appropriately.
So can you also identify when order doesn't matter?
Oh, true. Oh, yes. Okay, that's a good point. So that's essentially we are able to do some like post inference based on the predictive model. Then we can do like inverse problem to trace back what order, like what kind of data points is more important, what kind of data points is less important. Yes, that's actually all. All basket into this UQ, how this Gaussian process can be used. That's actually, as I say in the beginning, I think toward the data science, we should have system thinking from data modeling to decision making, not just do the modeling.
I guess we'll close it here. I just want to say thank you to Xinwei again for a great talk today. And thanks to everybody for attending this whole seminar series that we have for expeditions. We're going to take a break in December, so we won't have any seminars in December, but we'll be back in January, and our first talk of 2021 will be January 14th, and we'll have Anil Villakanti from UVA speaking. So thank you, everybody.
Thanks. Yeah, we look forward to more discussions.